Buenas tardes. Afternoon, folks. Don't know if you see the short where I did that. Dropped. Bang! On my toe, I kicked it. Ouchie. Right on the bone. A betrayal so dark, I would not wish it on my worst enemy. Not even on my worst enemy. That's all I'm going to say on that one. Right. 8 minutes and 20 seconds for light to reach us from the sun. Another 1.3 seconds for the light from the sun to reach the moon, and then another 1.3 seconds for that light to bounce back at us. So 2.6 seconds really, because we have to wait for the light to go from here to the moon, and then from the moon back to us. So if the light goes to there, it still has another stretch to go before the photons bounce back to the retinas of those watching. I assure you that when you're looking at the moon from planet Earth, you are seeing the moon exactly where it is. You're not waiting for photons. The sun's absolute light is shining on the moon at the very same time as anyone is looking at it. If sun turned off when everybody's looking at the moon, it would go black. It would all just disappear instantly. Then sun turned back on, bang, it would light up again instantly. There's no packets and packets of invisible massless photons on their way to anywhere. The grass is green. Red, purple, black. I think you'll find it's a colour, not just the absence of light. Now, listen to this. Where's the remote?
Way is gravity going to pull? Yeah. There's no direction for...
We're talking about measuring the microwave radiation, universe, yada yada.
Preferred. So there has to be something that says some spaces are different from others. So, okay, in that case, something's got higher density and something's got lower density. There should be hot and cold spots in the radiation. So that was a pretty definite prediction by the time we launched the Kobe satellite. Yeah. When we started conceiving it, there was no definite prediction whatever. We just knew we had to go measure.
Right. And so, is that a separate part of the measurement apparatus?
Yes, we had a whole separate instrument that was to make a map of the microwave radiation. And it was done with a more traditional microwave receiver technology with transistors and diodes and things like that.
And how accurate was, in other words, how big could the, or I should say, how small could the anisotropies be and still be measured with the device that you put up?
We measured anisotropy, which is a fractional variation of temperature, about a part in 100,000.
Part in 100,000.
So the temperature is about 2.7 degrees. That means we're looking for temperature variations of about 30 microdegrees, comparing one part of the sky with another.
Was that well within the...
Of course it was well within the boundaries. 30 millionths of a degree? That's nothing when you're measuring temperature up in the sky, is it? A microdegree. A microdegree. A microdegree is 1/1,000,000th of a degree. So we have 1 degree, we have, let's say, 38 degrees Celsius to 39 degrees Celsius. Between 38 and 39, there is 1 degree. And that 1 degree is split into 1,000,000 parts. Imagine that. Do you remember when I said, and I stand by this, as soon as they pushed the 2 atomic clocks in 1971, as soon as they pushed that 200 to 300 billionths of a second out, the floodgates were open. The people are loving it. The people are lapping it up, aren't they? Now, they're trying to measure or trying to spot the difference. 30 millionths of 1 degree. 2 points. So as we can hear,
Measurability of the apparatus?
It was just barely possible for us.
Okay.
In fact, our project was delayed for a while because the Hubble telescope needed more money.
money, 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 it's a rich man's world.
And so, okay, well, what are we going to do?
I mean, so you actually had funding that was cut because of
we
Hubble?
couldn't keep up. So
Couldn't keep up with the funding. Had to buy ourselves brand new cars. Dollars were everywhere.
okay, Hubble had very high priority for
Yeah,
that reason.
of course.
Okay, so what are we going to do? We've got another year. or two.
Hubble, and the Hubble, we know where the, oh no, we're talking the Hubble, I was thinking James Webb. Look, tonight, I was going to do it last night, but I couldn't motivate myself. Oh, look at that. See how skilled I am? All right, tonight was a full moon, not last night, the night before. I was going to do it last night. It was freezing and I just couldn't get motivated. I'm back, all right? The past is dead. Dead. Tonight, we look at the moon with the telescope and without the telescope. I'm going to do a moon night, get the fire going. It looks like it's going to be a clear sky. The moon right above me at 12 o'clock. Boom! So I'm going to get the telescope ready, come back, and I will say things like, when you're looking at the moon, you are seeing the moon exactly where it is. You're not waiting for photons to come down. Packets and packets of salt and vinegar and cheese and onion crisps. There's no such thing. We know this during the solar eclipse. When someone finds themselves in that sweet spot on planet Earth, looking at the moon, there's a line that goes straight through. That can only happen with absolute light. It's so obvious, it hurts. All right, laters.